Hey guys, welcome to session 4 of the Introduction to Data Science series, and today we will be talking about classification. In the last lecture, we talked about regression and mainly we discussed how linear regression works, what are some of the assumptions, and we also talked about regularization. So if you want to look at regression, please look at the part before this and make sure you understand that. However, this video is not related to that one, so this is an independent topic. We'll be discussing classification today, but the main algorithm that we'll be discussing is a logistic regression algorithm. Although the name of the algorithm has regression in it, it is not a regression algorithm, it is a classification algorithm. Okay. So let's start with an overview of classification. So if you're trying to predict y, right? And in classification, basically what we mean is what we are trying to predict should be a categorical variable, means it should be a binary variable 1 or 0, it should be a yes or a no, it can be colors, it can be anything which is categorical, and it is not a continuous variable, right? Just a refresher, a continuous variable can have any number on the number line, it is any real number, and a categorical variable only has categories. So y here can be a categorical variable and it's a function of x. So we are trying to use certain independent variables or predictor variables in order to predict y, which is our main target variable. The most common algorithm for classification is logistic regression, right? And this is how the equation looks like. So you're looking at a log odds on the left hand side, and on the right hand side it looks very similar to a regression equation. So beta naught plus beta 1x. So the main difference is the left hand side, where you instead of y you have the log odds, right? What is an odds? Odds is basically we are defining a success class. So a logistic regression today we'll be discussing for two classes, and a success class here is basically H, which is a high income class. So the example that we are looking at is we are trying to predict whether a certain individual will have a high income or a low income based on his education, similar to the previous example that we looked at. And the success class, the 1 in our example is the high income group and 0 will be the low income group. So in log odds always we consider the success class, so we have to define that first. Here we are considering the high income, so PH is the probability of an individual having high income, right? And 1 minus PH is basically the probability of an individual having low income. Why is that? Because probability of an individual having high income plus probability of an individual having low income should always sum up to 1. It can be either of these two, right? So PH divided by 1 minus PH, this is the odds of having a high income. This is how we define odds. Odds of having an high income, just to repeat, is probability of having a high income divided by probability of having a low income. And once we expand this, probability of having a low income is simply 1 minus probability of having a high income. We take a log odds. So we are taking a logarithmic function of this particular odds that we have calculated inside the brackets. In a general regression model, we use least squares, right? In an ordinary least squares model. But here in logistic regression, we'll be using maximum likelihood estimation. So this is a kind of a probabilistic estimation, and we'll discuss this briefly in today's video. Note that logistic regression is a type of a generalized linear model, right? It is a linear model. Why? Because in a linear regression, we simply have y is equal to beta naught plus beta 1x. But here, if you look at the right hand side, beta naught plus beta 1x, right? Just take this to be a variable a that is equal to beta naught plus beta 1x. And if we do certain transformations, right, to find out pH, it will be a function of a, right? So pH is basically a function of a, where a is a linear function, beta naught plus beta 1x. So a here is the sigmoid function, which I will show you later. But basically just to demonstrate that the left hand side, when it is pH, right, the probability that the logistic regression model is predicting, the right hand side is a function of a linear function, right? So it's a generalized linear model because there is a link function, that is a sigmoid function here. Don't worry about it. I just want to go over it briefly for those students who are advanced, who can understand this. So just a thing to keep in mind. And ranking is another application of logistic regression. So in classification, we are trying to say whether an individual is a high income or a low income. But in ranking, basically, if we are given a data set and we want to predict, which individuals have the highest probability of having a high income, and we want to rank that. Say, give me the top 10 individuals who are having the highest probability of having a high income. So we are trying to rank the person with the most probability, then the second person with the second highest probability, and so on. So logistic regression can also be used for that, and there we use lift charts, right? In the detailed video after this series, we'll be going over each of these concepts in more detail. Let's look at now the visual explanation of what a logistic regression looks like. As you can see on the y-axis, we have a low income that is denoted as 0. This is one category. And the second category of income is a high income, which is denoted as 1 because it is a success class in our example. And the low and high classification is done in the data itself. So we have not done anything. The data that we have gotten has mentioned high and low, and this is simply, we are just plotting it. The x-axis is the education, right? So you can see these data points. There are 5 data points with low income and about 8 data points with high income. Instead of a line in a logistic regression, you fit this squiggle. So this is a curve that you fit. And this curve will look very familiar because this is the curve of a sigmoid function, right? So it's not a good model if you're fitting a line to it. We are looking at a sigmoid function, right? And when you look at this equation, right, you're not looking at y versus x. So the left hand side is not y, it is the log odds. So there is a difficulty when we are trying to build this model, right? Because the values are constricted between 0 and 1. The probabilities are always between 0 and 1. That's why we use a transformation where we do a log odds so that we can use a linear function in order to predict, which is denoted by this equation. Log odds is beta naught plus beta 1x. So this is the transformation in the second plot. Here the y-axis is the log odds of high income and the x-axis remains education, right? Okay, just think, if the probability of having a high income, which is the y-axis here, right, is 0.5, what would be the log odds? The log odds would be log 0.5, which is the probability of having high income, divided by 1 minus probability of having a high income, which is 1 minus 0.5. That will basically come out to log 1. Log of 1 is 0, as we know. Don't worry about logarithms if you are not familiar with them. I will still be going over it, but you can skip these few seconds. At 1, when there is high income, right, the log odds is basically log of 1 divided by 1 minus 1. 1 minus 1 is 0, so denominator is 0. 1 divided by 0 is infinity, so log of infinity is positive infinity. At 0, log of odds is basically 0, which is the numerator, divided by 1 minus 0, which is 1. So log of 0 is negative infinity. I just want to demonstrate this mathematical concept because in this graph, all the data points with low income, if the y-axis becomes log odds, they become negative infinity, and all the data points which have high income, they become positive infinity on this chart, which has y-axis as log odds of high income. Now, it's possible for us to fit a line, right? So you can see this line. Here, you can see that we cannot use a least squares method because the distance will always be infinity from the data points to the line. So here instead we use a maximum likelihood estimation. Let me briefly go over how that is done. Here we want to find the best line, right? So what we do, we take one line, the algorithm takes one line and it projects all the data points onto that line, right? So once you project this data point, for example, onto this line, you will get a particular y value, right? For a certain x, you will get a y value. This y value is the log odds. From log odds, you can do a reverse transformation to get the probability. So log odds is basically log of probability divided by 1 minus probability, right? You have the actual number, which is the log odds. From there, you want to get the probability. So you can simply do a reverse transformation and get the probability. For this data point, you will get a certain probability. So then you come back from this graph to this graph, and you will not have this line. So you will get a particular value. Say if you come here, let's assume you get 0.25. So you're getting 0.25. You will see the y-axis and plot that there for that particular x value, right? Similarly, for another data point, you will get another value. You will plot that on this graph. So you will plot all the values on this graph, right? And it will look something like a squiggle. That's mathematically correct. Now, basically, we want to maximize the likelihood. So what we will do is, for all the data points with high income, we will take the probabilities that we are getting. Probabilities are called likelihood in this example or in this algorithm because we are not looking at area under the curve. We are just looking at the particular data point. So we'll take the likelihoods and multiply them for the high income group, and for the low income group, whatever probabilities we get, we will take a 1 minus of that value, because if we say get 0.25, that is the probability of having a high income on this y-axis. If you want to get the probability of having a low income, that will be 1 minus that. So we will get that value and we'll multiply all those values and get a particular likelihood value. We want to maximize that likelihood. So the algorithm in the backend tries to maximize that likelihood, and it tries to find that line which enables it to maximize the likelihood. That's how this particular function is estimated with these two parameters, beta naught and beta 1. That's how this estimation is done. Don't worry if you didn't understand this. This was a bit complex, and I will be explaining this in much more detail in the detailed series. So this is just to give you a flavor of what is happening, right? Okay. So we have estimated the parameters beta naught and beta 1 using maximum likelihood estimation. And now we want to predict. Say we are getting a new data point and we want to predict whether it will be a high income or a low income, right? Using this equation, we will get a certain probability. But say we have gotten a probability of 0.5. Do we classify it as a high income or do we classify it as a low income? We need a certain cutoff threshold where we can say that above this is high, below this is low. So that cutoff is found using the validation data. You split the data set into training, validation and test, right? On the training data, you have basically estimated the model. Using the validation data and a particular metric, right? Metrics I'll be going over after this section. So you choose a certain metric. You can just think of accuracy that we use in regression. Here in classification, we use another metric. Okay. So we just take a metric and we try to maximize the value of that metric. And whatever cutoff maximizes the value of that metric, we use that cutoff and then use that to predict. So if say the cutoff comes out to be 0.4 and we got a probability of 0.45, we say that it is a high income individual for a certain level of education. Okay. Now let's look at the evaluation part. This is where the metrics come in, and this is a very important area of classification because this is where most of the interview questions are targeted, and it's very important to understand and remember these concepts in detail. Here you can see a confusion matrix. This is basically on the x-axis you have the predicted values. So say the algorithm has predicted high income for a certain individual, but actually he had also a high income. So it will fall in the top left box. The algorithm predicted the individual to have high income, but actually he has low income. right? So this is what we are talking about on the training data set, where we know whether an individual is having a high or a low income. If the individual actually has a low income, it will fall on the top right box, which is a false positive. Top left is true positive, where it is a positive because our success class is high income, so it's a positive, and it's a true positive because what we have predicted is actually correct. A false positive means we have predicted it to be high income of the success class, but it is actually not. So it is a positive from our end, right? But the actual data is saying it is false. So it's a false positive. Similarly, if you're predicting low, right, and actually it is high, that means we are predicting low, it is a negative, but it is actually a high income. So it is a false negative, right? And if you're predicting low and the actual is also low, it's a true negative because it's a low and it's actually also low. So it's low, that's why it's a negative, and it's actually also low, that's why it's a true negative. So this is a confusion matrix which basically allows us to see how our data is looking, if it is skewed, if one class is skewed or not, right? Say if negatives are more in the data set, you will see false, so you will see, false positive plus true negative a lot. And if the data has a lot of positives, which is success class is very high in number, you will see a lot of true positives plus false negatives. So you can just look at vertically. If true positive plus false negative is very high, that means there are a lot of individuals with high income and the data is skewed. So we need to balance the data before we can run the logistic regression model, because the model will also not be able to learn properly. It will look at more data with high income group and less data with low income group. Okay, some of the metrics that we can now use from this confusion matrix are precision, recall, and specificity. Precision is nothing but out of all the positives that we have predicted, how many are actually positive. So out of all the high income individuals that we have predicted that they are high income, how many actually are? So this is kind of a precision, right? And recall basically means out of all the high income individuals that are there in our dataset, how many were we able to identify, right? So make sure you are getting this concept right, because it is very important. Precision and recall are one of the most frequently asked interview questions. Precision, to repeat, is basically what we have predicted to be a success class, right? Of all those data points, how many actually are success class? So for example, let me take a disease like cancer. A hospital is using an algorithm to predict which patients have cancer based on their historical data or probably medical data. Say they are predicting 100 patients to have cancer, but out of that only 60 have cancer, right? So precision will be 60%. Recall means that actually 150 people have cancer, right? And they are predicting 50 people to have cancer, which is a true positive, basically what I'm talking about. Sorry, 60 people have true positive who actually have cancer. So 60 divided by 150, right? That is basically a 40%. So 40% will be the recall in that case. Specificity is basically out of all the negatives that are there, how many does the logistic regression model actually identify? That is the specificity. So recall is also called sensitivity, and specificity is basically out of all the negatives, how many was the algorithm able to identify correctly. So it is true negative divided by true negative plus false positive. So there is a trade-off between precision and recall. Precision is basically minimizing the false positives. So it is a good metric to use for evaluating the model if we are concerned about false positives. Recall is more appropriate if we are concerned about false negatives, right? False negatives, false positives will all have costs associated with them, right? So for example, if we are saying a person is more likely to have a fraudulent transaction and we should not approve his credit card limit, or we should not give him a credit card at all, or give him a loan, for example, things of that sort. If the person is right and he has paid his bills on time, he is not likely to do that in real life, then, and the algorithm predicts that no, he's going to do a fraudulent transaction, right? That is basically a false positive, and that will hurt the sentiment of the customer, and the reputation of the company will be tarnished. So there is a certain cost associated with that false positive. Instead of false negative, will have another cost. If you are saying a person will not have any fraudulent transaction, but he actually is more likely and he does have that, so there will be a cost associated with that. So that's a false negative, that we are saying that no, he will not do a fraudulent transaction, but he actually goes ahead and does it, or he has done it in the past. So we can use a composite score where both of these are important, and it's basically the harmonic mean of precision and recall. So it's basically 2 times precision times recall divided by precision plus recall. If you remember how a harmonic mean works, mean would simply be precision plus recall divided by 2. Harmonic mean will be 2 divided by, in the denominator, the term will be 1 divided by precision plus 1 divided by recall. So when you just simplify that, it will look like this: 2 times precision times recall divided by precision plus recall. And this is the harmonic mean of precision and recall, which is the F1 score. You can also do a weighted average, right? If there are different costs associated with precision and recall, and that can also be used as a metric. So that's an advanced metric, and we'll look at it later. So this was all about logistic regression and classification. In this video, we looked at mainly logistic regression as the classification technique and went over very briefly all of the concepts that are very relevant to understanding and explaining this concept. It can be used in interviews. It can be used for your understanding of, when you're seeing the results of a code, how it is working, what numbers you are getting and how to make sense of them. So making sense of the numbers, of the results of the model, is very important in data science. And this is where these concepts come in. So coding is one part, but understanding the math behind the algorithms, what is happening, being able to understand them, that's where you should aim for. Thank you for watching this video. If you have any questions, please let me know in the comments below. And I will be posting a snapshot of this whiteboard in the description below. So if you're not able to read something on the whiteboard, you will be able to, look at it at your own pace. Thank you and goodbye.